and that I actually believe it will be discovered. I'm betting my money on that. But more important, I thought I should give you, and then I think it will be 2- or 3-fold useful, this example of how to break a fundamental discrete symmetry. And not just leave it up in the air as I did last time, okay? Some of you were asking, I think it was Nicolas, it doesn't matter, what really would be the Higgs sector? It's good to have an idea what it means to construct a theory beyond the standard model. This is a typical example. You need more Higgs, obviously. But let's see together whether we can figure out which Higgs it will be and how you break the symmetry. And I think it will be very useful because the problem with 2 vectors, the SO3 or SOM problem, I think nobody got it right, or nobody got it quickly. And this will be another illustration how to proceed when you have a multi-field situation. So we said we have this gauge group, SU2L. The reason is even more than the gauge group itself, is that this is the symmetry that you observe as a child. So we should understand what it means, okay? And we take us to some other interesting example. Remember we said we know what is U1. It's a physical contour number. It's a difference between baryon and lepton. Characteristics of the system. And we said that there had to be what we call the bi-doublet. How did we know? In this theory there are quark doublets, remember. So we are going to say left-right symmetry breaking. And also there is a right-handed doublet, we said. That's why there is SU2R. And similar for leptons. In order to give particle masses, we need Yukawa couplings. So we can start with quarks. Okay, the lepton situation is always more complicated. There is the issue of Majorana mass, the right-handed neutrinos, and so on. But in the quark case, we know it's a Dirac mass term, right? We don't want to break charge. Therefore, the Yukawa is obviously of the form QL bar, some Higgs. I'm schematic here. I don't have to write all the couplings. I just want you to give the symmetry, the Ponto number. So what is this guy? Q, or let's say fermionic left-right doublets. Fermion starts for quarks and leptons. Transforms like this, you agree? I'm glad we are all here today. I think this is really fundamental. Okay, and I'll give you another example in a minute. So that means that phi, let me recapitulate, transforms as, I get UL dagger here, so this UL, phi, UR dagger. Right, it's a matrix, obviously. If I had only this, it would be a column. If I had only this on the right-hand side, it would be a row. It's a column and row, it's a matrix, right? What we often, the way you will often see that people like to write the contour numbers. So they say it's a doublet on the left, it's a doublet on the right. You have 3 gauge groups, okay? You know how to read this, right? Doublet on the left, doublet on the right. Or anti-doublet, but remember in SE2, anti-doublet and doublet. It's a pseudo-real representation. They can be connected to tilde. Okay? What about B minus L, in your opinion? Does this field carry B minus L? How do you decide?
Is it 0?
0, right? Why? How do I know? Because it's coupled to Q bar Q. And that's 0. So when you introduce a new field, its properties are decided based on the properties of the fundamental fields that you started with. Our fundamental building blocks of nature are quarks and leptons. We know their numbers by definition, right? Quark is a baryon. It's good to remind ourselves, baryon number of a quark is 1/3. There are 3 quarks in a baryon. And the lepton number of a quark is 0. Baryon number of a lepton is 0 by definition. Lepton number of a lepton is 1 by definition. 1 lepton in a lepton is that elementary fields. Okay. So this is, or you can say this is a bit surprising because the doublet in the standard model carried U1 number. But remember here Q is T3L plus T3R plus B minus L over 2, which is T3L, what we call hypercharge over 2, remember, in the standard model. So actually this field does carry hypercharge. It doesn't carry B minus L, but it carries T3R. I just defined it here. It will carry hypercharge. Everything is okay. There's a doublet inside. So this is the first field which will go through the usual symmetry breaking. For example, the invariants typically would write like this, trace phi dagger phi, right? Since it's a matrix. When it was a doublet, you would write phi dagger phi, but now you can take trace phi dagger phi. That will be invariant. Trace, because you need to get rid of the extent. This transforms into the trace, UL. No, phi dagger goes as UR, phi dagger phi, UR. And that's trace phi dagger phi. So this stage is always easy. There is one new Higgs multiplet which contains your standard model doublet. You repeat what you did for the standard model there. That's not surprising. The question is what to do at the first stage, right? This was the question asked. I think this is what you asked me, actually, Nicholas, I think asked too. So, what should we take at the first stage? What is our task? What do we have to do? We have to now understand, once again, what Weinberg had to do in his classic paper, right? How do you reason? What is the choice? And what do you have to achieve? This field is obviously not sufficient because this field, notice it's left-right symmetry. It doesn't do what I want. I need to break this left-right symmetry. Also, this field being a doublet or two doublets, its scale of symmetry breaking is MW, by definition of a doublet. I need a new scale. So this was the idea, this G left-right. Once again, let's write G left-right breaks at the scale MR to a standard model, which breaks at the scale ML, which is actually MW, if you wish, to U1. So here, we are here. And how do I reason? Well, I say, at this first stage, I need to break only SU2R. Right? I need to break SU2R. I need to break U1 also, but I need to break SU2R. So that means I need a multiplet that is a multiplet of SU2R, but not of SU2L. Because if it's a multiplet of SU2L, it will also break SU2L. Okay, you're following me, okay? Please ask any question here, okay? That's silly as it may look. So I need a multiplet, let me call it delta R. I have phi already, so, okay? Some new name. Is this clear? And maybe it's a doublet, maybe it's a triplet, maybe it's a quintuplet, maybe it's 155-plet. Okay, we'll think a little bit in a second. And by definition, because I'm saying that the world is left-right symmetric, so in other words, the gauge group here, there is a left-right symmetry. This is what I mean by left-right symmetric one. Delta R requires the existence of delta L. So what has to happen at the first stage? I don't know whether I can achieve it. What has to happen at this stage? The delta R gets a vacuum expectation value, which I can call VR, you agree. And delta L must get a zero vacuum expectation value, because at the first stage I cannot break SU2L. Then I will get a big mass for the W boson. So I have to achieve this. This is what I mean by the spontaneous breakdown of left-right symmetry. They're connected by left-right. And before I specify these multiplets, let me show you how this would work. Once you figure out, because it's messy, imagine if I have some big multiplets, it's a triplet, then it gets messy to see what is going on. This is not just the usual. I have to take second derivative and so on. And I don't really know what, what is happening. So here is the argument. In fact, generically what will happen is the following. There will be terms like a mass term, which, remember, in order to achieve symmetry breaking, I need a mass term. Let me be schematic, you know, these are multiplets. This is some delta R, dagger delta R. But the bottom line, to capture the essence, or imagine they are just scalar fields for simplicity. You agree I need the negative mass term in order to achieve vacuum expectation value. That was the message that Higgs, Goldstone before, right, gave us. We have to start with a tachyonic field. Agree. Because of left-right symmetry, there will be delta L squared. They must have the same masses. This is the definition of left-right symmetry to start with. Okay, everything has to be symmetric. Okay. Okay. Then I go on. There must be self-interaction. If I want to break, if I want to get, in any way, I should write all the gauge invariant interactions. But remember what we said? All the working possible terms in my theory. So there is delta R to the fourth. If there is delta R to the fourth, there is delta L to the fourth. Remember, these fields carry gauge quantum numbers, so there will be no linear terms. You won't write delta L or delta L cube. Okay, these are doublets or triplets or whatever. That simplifies my task. I want to get generic features, but they may carry quadratic terms just like here. Therefore, I may get here some lambda prime, delta L square, delta R square. These should capture basically all the possible interactions, whose form may be a little more complicated depending whether what type of the multiplet this is. But it's going to have the form like this. And this was the problem that you had with two vectors. Remember, there was a potential that depended just on the vectors themselves separately, and then there was a term that knew about the relative orientation. Let me normalize it like this. This is very similar. I'll comment on the two vectors in a second. Mehmet.
Those are actually inside the phi doublet, or what did you call it? I don't remember. In the matrix form. You could represent this, right? Or expand the trace of phi dagger phi into something like this.
Well, phi has nothing to do. Phi I will treat later. There is no phi. I'm at the first stage.
Okay.
Just think of the scale as being very large. Okay, at this point, standard model cannot get a vacuum expectation value. I'm allowed to separate this into different, if you wish, tasks. At the first task, well, of course, I write the whole potential, and I send you a page, okay, just that you see it gets messy, okay, but it can be dealt with, surprisingly, actually fairly neatly when you struggle after a while. But the point is, I know that this stage phi has a zero vacuum expectation value. That means that the scale that corresponds to phi is very small. I can put it to zero by my usual argument. Remember, it's when I deal with the situation, then I do perturbation theory always. The particle is very light, I pretend it's massless, then I turn on its mass. But first I go step by step. This is the way we proceed. I need to understand how I would do this without, breaking my head too much. How would I see elegantly that the parity can be broken? The reason I'm telling you this, when I decided to look into this was my first paper. Actually, I found out that Pati Salam, great physicist, okay, and Mohapatra and other people said that this cannot be achieved, that you cannot break parity spontaneous. And this is trivially easy, surprisingly. But to me, it took some time to understand what was going on.
When we write LR, do we mean that we have an extra symmetry?
Yes, this is the symmetry. Maybe you can call it parity.
But
For example, the symmetry between left and right we often call parity.
why it's not included just?
No, because I'm saying that
Yeah.
the couplings are the same. I would like to break this symmetry spontaneous. I believe the nature is left-right symmetric at the fundamental level, and I believe that the breaking that occurs is spontaneous.
I mean, for example, if we just break like the right one, the SU2 right.
It's not if you break. Before breaking, when I write my covariant derivative, okay, my covariant derivative looks like this, okay? This is an important question that Mahmoud asked. Let's get it clear. It would look like this, you agree, GL, TA, let's call them L, A mu L. There are some gauge bosons, so I'm writing in the real notation before I introduce complex W and so on, minus I, there is A here, right? GR, TAR, A mu AR, and then there is also minus I, there is this G prime over 2, right? Or GB minus L, if the symmetry is B minus L, be the corresponding gauge boson. Okay, this is not so important, this is important. Now, in general, when I write this gauge group here, if I don't say anything additional, GL is different from GR. And parity is broken immediately. There is nothing to discuss. This is the picture that Weinberg, Gleschow, they envisioned. They didn't say that there are no new gauge bosons. They knew there could be. But if they are there, according to them, they will have nothing to do with the standard model scenario. There will be some new couplings, new fields, and so on. This was the idea of the standard model, that the parity is broken to start with. Okay, you live in an asymmetric world. So what I'm saying when I call this a left-right symmetric theory, this is the definition of a left-right symmetric theory. What we call G in the standard model. There is a V coupling, but it's the same on left and right. Therefore, I have to achieve the breaking spontaneously. The symmetry is badly broken. Now I have to study the same issue that you needed to face in the standard model. There, nobody was massive. We had to generate the mass. Now I need to generate mass for the right-handed sector. I will pretend I'm at this stage. Remember, at this stage, I'm separating the stages to answer your question, my friend. Here I pretend that standard model is a good symmetry. I'm before Weinberg Salam. I'm before these guys. I just have to come here.
So, just to be sure, these deltas are different Higgs particles, right?
Sorry,
Those deltas.
they have nothing to do with this field. Here is the standard model doublet. There is actually another doublet, which I argued is very heavy. And that whoever wants to study this deeper one day, I could show you, we let's not enter into details. This sector here, of these doublets, has nothing to do with this sector here. They will talk to each other eventually, but nothing to do. They are separate fields. This is what you mean by complexifying the Higgs sector. In the standard model, you could do with just one. It cannot be. Any gauge group you take, you may want to study granular unification tomorrow, you will need a complicated Higgs sector. The more beautiful the theory, by the way, the more elegant. There is something we call SO10. Beautiful, very unified, Fermi has unified everything. It requires a very cumbersome Higgs sector, obviously, because the more it does, the bigger it will be. Therefore, more breaking will be needed, therefore more Higgs will be needed. That's the struggle. Where is the beauty? In the original theory, right? Or in the simplicity and predictivity? You know, it's up to us to choose. You and I can stay at the standard model forever, but remember, neutrino is massive. And I wanted to come with a theory which was actually there that predicted all these properties of neutrinos, mass oscillations and so on, okay? And I'm giving an example here.
So when we're saying that parity will be broken, we're saying that GL and GR will be different first, and then...
well, even if they are the same, no, not necessarily. There are two ways of breaking a symmetry, remember. You can break it through different couplings or through different masses.
But let me also...
For example, in the standard, I gave you an example of, remember when we studied SU2? we said maybe the weak interactions, electroweak, are described by SU2. Remember, we tried. This is how this course started. I said, let's try this. This was before Glacial, or before Weinberg, Salam. So we said maybe, and here there will be W plus, W minus, and the third guy I wanted to be a photon. I wanted to have the minimal theory. And here, of course, there is one gauge coupling. GW is GA, which is G, because there is one gauge group, which has its coupling G. But yet the symmetry between W and A is broken badly, and it's broken because they get completely different masses. So two ways of breaking the symmetry. Either you start or achieve different couplings, or you will have one and the same coupling, but you achieve different masses. We call it breaking soft. Because why is it soft? As you go to higher and higher energies, you will get more and more symmetry because the couplings are the same. Imagine when I go to the energies above this breaking, I will recover the symmetric world. I will actually see the idea I started with. And this is what was achieved in the standard model. Then it was made complicated by SU2 plus U1, but when we go to higher energies, when we go to LHC, the difference between the photon and the Z practically disappears. They're both effectively massless, you agree, that there is very little difference.
But I mean, when we add this parity new group to our big Paul group, do we mean that the field transform like the field itself go to minus the field itself, then the Lagrangian will be
minus?
invariant?
What do you mean minus? The field transforms the way, here is the way the field transforms. This is an example. This is an example.
Yes, but I mean when we add the parity as a group of the
when I add this additional discrete symmetry that I call parity, okay, then this is a transformation property. Not minus sign. Oh, this was an example of, remember when I took a discrete symmetry, it was phi going to minus phi. That was the most trivial example. This is more complicated. Here I need two fields, but they go into each other by this symmetry. So you see, the potential is completely symmetric, the couplings are completely symmetric, everything is symmetric. And according to this theory, the nature, you should see everything symmetric between left and right. However, if this takes place, then the opposite will happen. The nature will become completely asymmetric at this stage. So here is a catch that you will do whenever you have a multi-Higgs vector, which I gave you with those two triplets to see if it's a tricky thing. You have to think. So look, in this case, for example, I can write this in the following form. I'll do a trivial Do you see what I have done? I completed the square. So I had to subtract a cross term. Okay? I can see Mahmoud struggling here. You see what I've done? When I complete the square, I get 2 delta L squared delta R squared over 4 is the same factor of 2. And now goes the reason, the same reason that you were supposed to apply in the problem with 2 vectors. Remember when the analogy with 2 vector problems, there was a potential which depended only on the vector phi 1. Then there was a piece which depended only on potential phi 2. And then there was a piece, which I called maybe lambda 4, I don't remember, doesn't matter, which actually knew about the relative orientation. And the thing was to conclude, before, if I put lambda 4 equal to 0, I can never know what happens really. This and this guy don't talk to each other. Actually, I even have more symmetry. So here was the crux. If I want to minimize the energy depending on the sign on lambda 4, for example, if lambda 4 is bigger than 0, in order for energy to be minimal, since this thing is positive, phi 1, 0 should be orthogonal to phi 20. I conclude. I conclude that the waves will go in the opposite direction, lambda 4 is negative, without any effort. I don't have to take second derivative and so on. I can do that later on, but I will have to get the same result. If lambda 4, however, is negative, I want to get as much as energy. This doesn't know about relative orientation. It doesn't care. I'm not changing this at all. This energy here, this static piece, is oblivious of the orientation. Whatever the orientation, you get the same energy. So here the energy deciding minimization, it comes from here to start with. You say if lambda 4 is negative, then phi 10 should be parallel to phi 20. Because that way I get as much as of negative energy as possible. And I have two cases to analyze. Lambda 4 equals 0 is not a stable point. It may appear in higher orders. We don't want to live on that unstable point. At that unstable point, anyway, we can conclude there are two independent SO3 symmetries, and there is nothing to do. Each of this would be as the one we did in the class. In each case, phi 1 will break SO3 1 into SO2 1. This will break SO3 2 into SO2. But lambda 4 dictates symmetry breaking. Okay. This was the idea. I hope we share it. I did discuss that with you. Okay. It was as simple as that. You know, the homeworks, I try to mix that. I give you some straightforward, but sometimes long, tedious exercises, right? Sometimes things to recapitulate. And occasionally a problem or two that sort of should be tricky, that should make you suffer, or that you won't solve, okay? We have to sort of see if we can take you. So maybe we'll do the same thing at take home. I'll give you a nice example of symmetry breaking, which is not trivial, okay? You don't worry when you don't get frustrated. So look here how you reason. You agree that this does not know who gets the vacuum. Suppose that I don't have this term. Then there is no way of answering what happens. These are things where you have a flat direction, okay? In other words, here, all I would learn from here, notice that a delta R squared plus delta R squared, call it 0, the waves, would be equal to mu square over lambda. It will have to be non-zero. This is a typical example. This is like having one field, call it, I don't know, delta square. And this is delta square again. And you I will never know who gets a wave. Did delta L get a wave or delta R get a wave? Or both get a wave. Okay, there is sort of a flat direction, we say. There is not enough information, okay? Without this term, it's not clear. It's irrelevant. So everything is, the fate of the theories in the ends hides in this term. There are two possibilities. Let's check them. The same thing that you were supposed to do for the lambda prime minus lambda could be positive, you agree? What will happen if, well, let me take negative first because it's not what I want. If this is negative, and I want to minimize the symmetry as much as possible, I want this to be non-zero. Let me write like this instead of. Remember the vacuum expectation value, we either write as phi 0 or the vacuum expectation value. This is actually a field sandwich between the vacuum states when you do it properly quantum mechanically. It reduces at the classical level to the minimization of the potential. You agree this must be non-vanishing in order to minimize energy. And it will be an easy exercise to see that they will be equal because everything is symmetric. You will have symmetric equations and they will give a symmetric solution. There is no way there will be a difference, okay? In this case, let me just say, you will conclude actually that these two are equal. In this case, left-right symmetry would not be broken.
Could we really consider the case where this term equal to 0, where we can just write a big delta and manipulate that? But at the same time, that delta.
You could, that's living dangerously, because what somehow, what is the crux of the field theory, the normalizable field theory we are dealing with, is that there will be infinities. You're learning that. When you look at QED, there is an infinity. If you look at that vertex corrections, it's infinite. So what you do, you absorb the infinity into redefine. You're saying, well, the infinity is coming because I have clouds of virtual particles, okay, so I have to redefine my original coupling. Well, infinity. Infinity if the cutoff is infinite, but maybe some huge number if the cutoff is large. So if I say that I have some lambda phi to the fourth, and I say, oh, maybe lambda is 0, that's what you're saying. That's similar, this, in the case of one field. Be careful, because there will be terms, and if this phi is coupled to fermions, psi bar, psi phi, and you want to couple to fermions, then there will be this Yukawa coupling. You will get immediately a diagram like this. Yukawa, 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 Yukawa. Notice, or do you notice? Did you study such diagram? Did you have a in the?
Or photon.
No, I mean in the scalar case, you didn't. But you can imagine that this is logarithmically divergence. Can you see that? Remember power counting, it's very useful. D4K, floating momentum into loop. Okay. I have how many propagators? 4. I'm looking what happens at higher energies, right? I can ignore the masses. This is k to the 4th. So this goes as d4k over k to the 4th. This is proportional to the logarithm of. It takes a second. So actually, you cannot live at the point when the couplings are equal to 0. They get generated. This is not a stable point. You may say that the coupling is positive. That's okay, because the contribution is what it is. You will absorb that anyway, but you can't live on 0. Don't do that.
I was going to ask, in that case, we have somehow a bigger symmetry.
You have a bigger symmetry. That teaches you, of course, that a bigger symmetry, this can be very useful, because when you have a bigger symmetry and you break symmetry, you will have some Goldstone bosons. So this is useful in the following sense. When you later on calculate your masses of your particles, then you have to see that in the limit lambda prime equal to lambda, you get some massless particles. You should use this. I mean, a few years ago, I restudied this potential with Juan Carlos Vasquez, who was actually our diploma student some years ago, and Alessio Maiez, our collaborators. And we wanted to really do this Higgs potential. It's complicated when you write all the terms, you can imagine. And then we wanted to compute the masses. And that gets very messy. But it's very useful. You can guess a lot by using these kind of questions. You are saying, go to various limits when you know there will be more symmetry. Then you should have Goldstone bosons. Then you immediately say, aha, my mass must be proportional to that parameter. Okay, that's already easier to start with. You use that. But don't leave on that point, because that's not a physical theory you're after. Now suppose that lambda prime minus lambda was positive. After all, I don't know what the parameter space is. To remind you, what we did in the standard model, maybe it escaped. Maybe it escaped you. Let's write down here the standard model. The standard model potential was. Let me write it again like this: mu square phi dagger phi. And there was a question of sign. Plus lambda phi dagger phi to the 4th. Let's put plus minus sign. Square. How did we reason here, remember? We said, we just want to remind you that you always choose a parameter space that corresponds to the physical. to the physical theory in question. First, you argue, oh, I cannot take a minus sign. There will be no ground state. Then you said here, well, I don't know what sign to take. Now there is ground state with both plus or minus sign. So we tried plus sign. And then with the plus sign, we got phi 0 equal to 0. That didn't work. Gauge boson remained massless. Then you say, no, I'll try minus sign. Then I got phi 0, what I call phi, equal to mu square over lambda. Oh, good, we said. Same thing here. I'm saying I could have tried here also plus sign. I don't want to do that. I won't get a web. That I learned already. I was told by Higgs, by Goldstone, by Nambu. We are standing on the shoulders of giants. That's new. He says. I remember someone said, I could have done much more. The problem was that I have all these giants standing on my shoulders. We have that too, remember? Where we get blocked by. Anyway. Lambda prime, lambda 0. Took me a long time to arrive to here. I was beginning graduate student. I didn't know anything, by the way. I had to learn gauge series and whatnot. But also I didn't know how to think, and I was looking at this complicated potential. And the solution was trivial. Lambda prime minus lambda positive. What happens here? This energy is positive. Remember, this does not know about orientation. So I don't even look at this now. I look at it later when I want to find all the correct expressions for the wave. But conclusion, this must be as little as possible, and that's 0. So here I conclude that either delta L is 0 or delta R is 0. They cannot be both 0 because I have minus mu squared. The second derivative is negative there. That's called the local maximum. But one of the two must be 0. That's what I call left. That's the definition of left. Remember that here, left will be decided by us. Whatever didn't get broken, we call left. Okay, there is a question of choice. In other words, you have equal probability. You know, you put a ball. You have two valleys on, and the top of the hill. You put the ball here. It can fall down in either with equal probability. For example, if I go back to the early universe, when I get enough energy or temperature to put it back, then I would say, oh, there should be some domains in the universe probably when the world is left and the others when the world is right. You know, there are interesting implications to think about. But the point is now, in our case, we say this. We have achieved it. All I need to do this. Just like Higgs saying that lambda is positive. Higgs said lambda is positive and I have minus mu squared. We would say true, lambda is positive. Mu square is positive here, I put a minus sign. But also, I will say lambda prime minus lambda is positive. This is our parameter space. You better check that the potential is bounded from below. You have to find out that you get a local minimum. You will compute all the second derivatives, these are particle masses, and so on. Okay, there is work to do. But now you can be reassured it should work because the physical argument tells me, just like in the case of two. Or the vector, did I send you the solutions to the two vectors? Well, I'll send it to you. I forget. I didn't send you to solutions to all the problems. I had these solutions. I must have sent to Visher, but not to. Okay, let me.
The other one is also a possibility, but we don't include this because it does not break down to the standard model. The negative.
No, right? You say I live here. Just the way Weinberg said, and Higgs, I live here with a minus mu square. There was a possibility, of course. We live in the half of the parameter space. There are some people who say that this is actually a deep question, why do we live? There are a lot of people who will hear that there is a sort of profound question in the standard model, or even a problem. You know, why is this sign negative? I find that question strange. If it was positive, then I would ask her, why is it positive? I mean, the theory lives normally on one point. Here I live on a half of the parameter space. I think that's a lousy question. This is very strange. When people worry about that, then they start with lambda positive. I remember the distinguished speaker worrying about this, so I remind the speaker, well, why don't you then ask yourself a question, why is lambda positive? His answer, it was he, not she, well, lambda has to be positive, he says, for the theory to be. Well, I said mu square had to be, you understand, it has to be like this, okay? That question, you know, think twice about asking these sort of Einstein-esque questions of, you know, why? Of this sort of, when you ask yourself questions, then almost every Dick and Harry in our field goes on and say, right, and appear in the seminar, say they want to understand why cosmological constant is small and so on. The probability that you and I understand such divine questions is very small. It's not that physics you answer, you go into that. You try to relate different physical phenomena. That's what good theories do. Why alpha is 1 over 137, I would leave to the end of physics. Maybe you say you come one day when you understood everything, now you want to know why the numbers are what they are. Anyway. That's the first step, or theory step. It can be a sheet. Parity can be broken spontaneously. I'll just say a few things. You and I will have to think a little bit, what should I take for these fields? They should be representations of SU2R. And obviously there should be some small representation. We don't want to work with 155 plets or whatever. So you could say, well, they could be a doublet, right? Delta L, delta R. A natural thing to ask, doublets. They could be triplets also. See, Weinberg had a dilemma, is phi a doublet or a triplet? Then it was easy to answer. It had to be a doublet with one field because he needed to give the mass to the fermions. But this guy doesn't give the mass to the fermions. So I don't know how to answer this question a priori to quarks. I don't want to really go much deep here. There are two possibilities, both can be studied, because you have to study. You don't know. If it is a doublet, delta L, delta R, then the only field coupled to fermions is phi. Therefore, here you predict that neutrino is Dirac. Remember, I am taking a fundamental theory. I cannot write some Weinberg operator and so on. That Weinberg operator is supposed to come out of my theory if it exists, okay? But if I say that delta is a doublet, it will not couple to leptons. Doublet cannot couple to doublets. The reason the standard model doublet couples to fermions because the right-handed quarks are singlets. Doublet, singlet, doublet is invariant. But think of this, if this is doublet, what can it couple to? Doublet, doublet, doublet doesn't exist. So I will conclude that neutrino is Dirac, and it's worse than that. In this theory, there is no difference between neutrino and the electron. In the standard model, there was a huge difference. I didn't even have to put nu R. And I typically would conclude here that the neutrino mass is the order of electron mass. We were stuck there. It was hard to understand why and how neutrino would be like. The solution is here. Maybe this is a triplet. I'll just comment here. Why? Imagine the deltas are triplets. Well, now you should actually, you've learned a lot, so maybe you would see this It took us years to arrive here, literally. I wanted to work. I started working, and people told me I was wasting my time, neutrinos and masses anyway, so, you know, it's hard to really work. But the funny thing is, when I was trying to understand the neutrino mass, I was thinking, at that time I didn't know anything about Majorana neutrinos. Nobody talked about that in the 70s. In the 50s, people talked a lot. They looked for manifestation of lepton number violation, didn't find it, and then simply got forgotten. And I was getting stuck here. The solution is simple. If delta R is a triplet, there could be a coupling like this. LR transpose I sigma 2 delta R charge conjugation plus, of course, right goes to L. If it's a triplet, why? I'm using the adjoint representation for the triplet. Remember, in the adjoint representation, delta R transforms as UR, delta R, UR dagger. Remember how we did a triplet? We said this would be very useful whenever we want to work with SU2. It's an adjoint Hermitian, it's a Hermitian matrix, traceless. In other words, delta R is Pauli matrix is sigma I delta R. There are three fields which we call the vector, and we expand in the basis of Hermitian traceless matrices, Pauli matrix. You can normalize to the generator. That's just normalization of a field. Let me not go into the detail. Okay, it's easy to see that this is invariant. The usual way we reason, we need this I sigma 2 because there is a transpose here. Now let me complete. Let me show you. This goes. This is enough to look into that. This goes into LR transpose, UR transpose, I sigma 2 charge conjugation. Delta R goes into UR, delta R, UR dagger. And then I can put C wherever I want. Remember, C is in the Lorentz space. Actually, when I do this, I don't write C. I don't work on that as much. And then delta R goes into UR delta R. So this is 1. This is LR transpose. Remember, I pass I sigma 2 on the left. This becomes UR dagger. And we use this rotation a lot. This property of Pauli matrices. The anti-commutation. Yes, please.
Did you say to write mass term equal coupling for the doublet case is not possible or possible?
Sorry, the what?
For the doublet case?
No, it will not couple. How can a doublet couple to? There is nothing to write. You see, a product of two doublets can be a singlet or a triplet. That you've learned from quantum mechanics. When I have a spin half, I can get spin 0, spin 1.
So the right-handed ones are now doublets, so it changes the
It changed everything precisely. And this is somehow why one never thought of triplets. Triplets were something unimaginable. In the standard model, we were hung out on doublets for a long time. Not just me, Salam, after showing that parity can be spontaneously broken, people got excited, and somehow the field took off, and this became an important alternative to the standard model, became the most popular, if you wish, theory beyond the standard model. But yet, someone was hung up on these doublets, and everybody would say, well, but your neutrino, you cannot tell me why neutrino is light. I would say, well, be patient, and they would say, I'm not patient, okay. So shut up, and there was a struggle. And now there is UR dagger, UR. I can put C wherever I want. LR. This is 1. So this is invariant. Well, that you've learned. I can put a singlet here, of course. But I can also put a triplet, okay? Out of 2 doublets, I can get any variant. The thing is, of course, here, this would never be a singlet because this carries hypercharge. You know, there is also a term, LL transpose, I sigma 2, delta L, C, LL. Delta L has a 0 vacuum expectation value, therefore it doesn't contribute to anything, okay? I showed you. I mean that portion of parameter space. But I want to tell you, this is sort of the analog of that Weinberg operator. Weinberg said, I can get a triplet out of 2 doublets. What Weinberg did, and that's why we go to V square. We wrote that triplet out of 2 doublets. We wrote phi, if you remember. The Weinberg operator was like this, L transpose C, I sigma 2 phi, phi transpose C, I sigma 2, why C? What C? C is here. Phi transpose I sigma 2L, writes Weinberg. I can shuffle this if you wish. That probably will be a take-home exam. I can write this as L transpose I sigma 2 sigma L. I remember Kevin checking it while I was talking and saying, you somehow seen this triplet. And then there is phi transpose I sigma 2 sigma phi. You can reshuffle it. You can show.
C in the
Emilio.
first term.
Sorry?
We have C in the first term.
Yes, good. So you see, this is effectively a triplet. You can also introduce a triplet. I said, now you say, oh, I want to get Weinberg's operator, okay? Immediately people write model building. You know, someone will write a paper saying, oh, I will introduce a triplet and give this delta L. Forget this left-right symmetric theory. Just introduce the left-handed triplet, give it a small valve. The neutrino will be light. This a posteriori model building, I don't want to discuss here. Anyway, I think I should slowly stop here. This is the theory. You see, I now get the mass when I write this delta R. This is what you were asking me. I don't know who last time. Who does delta R in new field gives a mass? WR, for sure. That's an SU2R triplet. It will do the. That we can do even as a homework, some triplet example, so that you see that, for example, remember we got a prediction between W and Z mass using a doublet? That mz cosine theta is mw. There will be a similar relation, but not exactly the same, because it's a triplet. So delta R, in other words, here is your answer. Delta R gives masses to WR. That's almost obvious. This is a multiplet, so gauge bosons get a mass from the covariant derivative. But also, I think this was Mehmet asking somewhere, also N will get a mass, it's here. When delta R gets a VEV, and the VEV, of course, has to conserve charge. But you can always do that, you see, it will conserve charge because I can rotate the VEV in the neutral direction. That direction I will call neutral.
We could in principle write the delta R mass torque with the UD particles that get mass through delta F, right? Mathematically.
Sorry, here?
Yeah, we could try to give, yes. In that
Yes, just we got the delta L is 0. This analysis, the symmetry breaking that I showed here, delta L is 0. My problem is that if delta L is non-zero, it will be equal to delta R. I will have a completely symmetric solution. I have two possibilities. Either parity is unbroken, really unbroken, that's bad for me. Or if it's broken, it's really broken. Delta L is 0. That's good. But it also tells me that nothing interesting happens here. I can forget about it.
What I'm trying to ask is, in the second term, the right-handed guys, how can we be sure that it selects only those new particles that we didn't observe, but don't select UV?
Well, there are two ways of doing it. One is by checking it. And you should do that, by the way. You know, you don't, imagine you're writing a paper, you do both. You don't just reason. But we can reason here the following. This is a, say, some multiplier. There will be a vacuum exponential value in a certain direction. I will call that neutral. That will be a definition of my charge. That's what I done in the standard model. Remember, in the standard model I introduced. Do you remember? The good thing is about having to do this once seriously, that you really understand what you did in the standard model. Because you don't understand what you did in the standard model because someone else did it for you. You never understand what people teach you. Or you understand, but never really as deeply as when you have to do it. Remember, doing physics means doing it. So, in the standard model, just to remind you, phi, I rotate it in one direction. And that was neutral by definition. By my convention, I called Q T3 plus Y over 2, and I said Y of 5 is 1. That was my convention. By that convention, this was neutral. With these conventions, phi is phi plus phi 0. I set my convention, then of course I rotate the value in the neutral direction, okay? I can do that. Since I can do that, that means it will always be preserved. I can always choose a convention that this is neutral. I will do the same thing for delta R, of course. Okay, so delta R is neutral. Since the delta R doesn't break charge, then only neutral particle can get the mass. I don't have to do the calculation, but it will go like this. You would write this nu R transpose, ER transpose. Then you would write this by the way, what are the, this is a triplet. We just said this is an SU2R triplet, which I wrote, remember, as an adjoint. Well, it's good that we remind ourselves of the adjoint. Hermitian traceless matrix. What about B minus L? What about the U1 number? Can you guess it? Can you tell me what it is? In the case of phi, it was 0, someone noticed, because I had bar. But here actually it's not 0, it's 2. Precisely minus 1 is plus 2. And in other words, B minus L acting on delta R is 2 delta R. And the charge is T3L plus T3R plus B minus L over 2, which is 1 for delta R. T3L is 0, you agree. This is an SU2R multiplier. So the charges of delta R, how will delta R look like? If B minus L was 0, then these will be neutral. T3R let me remind you, I can erase this. I'm assuming this mastery of group theory, which may not be there. I've been appealing to you, make sure you master it. When I say that the representation is adjoint, and that means delta R transforms as UR, delta R, UR dagger. Remember, this is equivalent to saying that the generators, let me write formally, acting on delta R, will act as the commutators. On the left, on the right with the minus sign. That's a commutator. And the generators, we know, these are Pauli matrices. The idea of a joint, you build everything with a fundamental representation with a doublet, and you just write in a matrix form in order not to introduce more complicated thing. That means that when T3R acts on delta R, it acts as a sigma 3 over 2 delta R. But this is diagonal. Therefore, it acts as a 0 on the diagonal. Okay, let's just take a neutral joint. We did it. You had this as a homework. I think we had an adjoint. No? You sure? You were asked to show that adjoint and vectors are the same? No? We didn't in the class, by the way. I showed manifestly that, okay. So it's easy to see that a triplet, call it any triplet, will have this distribution of charges, 0, 0, plus and minus, through the commutation relations of okay, this is where sort of sigma plus lies, and this is where sigma minus lies. But there is B minus L, which is 1. So the charges go like this, plus 1, delta R plus, minus delta R plus, remember it's traceless, delta R plus plus, and delta R 0. You shift the quantum number by 1 unit. What was previously neutral, and here there will be a charged particle, okay? How does the triplet look like? How does a triplet look like? Anyway, remember pi on pi plus, pi 0, pi minus. But now I added, this is a neutral triplet, I added a U1 charge. So now I've shifted it. I have pi plus, pi double plus, and pi 0 because I've done that. So I'm predicting a new type of particles, doubly charged particles. They're very interesting. The physical design is mind-blowing. For example, delta R minus minus, if you produce it, is spectacular. It decays into 2 electrons. There'll be a direct lepton number violation that you will see in the theory. Yes?
When we boil down to the standard model, we need to recover the doublet Higgs, right? From this.
Not from this guy. The doublet is in the bidoublet. That was okay. I mean, it's. If you wish that task about the standard model breaking there, what I do is kind of trivial. In every theory beyond the standard model, I say there must be a doublet. I just embed it in the minimal representation of, for example, suppose I told you, you and I have to build a theory based on a group called SU5. And I ask you, where will the Higgs doublet lie? I need to have a Higgs doublet to break the standard model symmetry. Let's say SU5 will be broken to standard model, and the standard model will be broken down to U1. This is called FW. And here the different notation is used MX. There is no rack in this guy. This is called MX on U-gauge boson. The scale is called X. So you say here I must have a doublet, you agree? Where should doublet live? What is the minimal representation that has a doublet of SU2? It's a quintet. I would know immediately. The Weinberg-Salon doublet must lie into a quintet representation of SU5. Quintet has a doublet by definition. That's what you did in SU3. In SU3 you took a triplet. You know, when you were thinking about SU3, there was always a doublet hidden. You know, when you build the SU3, how did you build it? With Pauli matrices, with the gamma matrix. But what is, for example, lambda 3 of Gell-Mann? There is an SU2 subgroup. So in this, what would be a triplet of SU2, there is a doublet hidden, okay? So let me ask you here in SU5, what will you choose here? What representation? The gauge group is SU5, here is SU3, cross SU2, cross U1. This is a digression, we are relaxed, we are finishing the class. This is not, I don't want you to learn this. I want you to relax, you know. The rank of SU5 is 4. The rank of standard model is 4. So here I will use the HEP that doesn't break rank. We've learned that, if you remember, it was a joint, okay? So here, you know, every time you have to struggle, it's a knowledge of physics, of group theory, and so on. It's not trivial, that first stage, but it can be done with some thought, especially if you have a collaborator. Then it becomes much easier, you talk to each other, okay? It requires sometimes really having a listening board, talking to each other to know. Because then, you know, doing a calculation, we can do it, each of us, on our own. Understanding what's going on, it's not easy on our own, always. Anyway, here, by rotation, the wave will go here. That's a definition of my field that takes a wave. I can always rotate the triplet in one direction. So if I put it here, I have I sigma 2. It looks like this. Notice the direction was picked up by where the wave went. I rotate in that direction, and that I call neutral. Okay. The thing, you know, the same way when I broke that field delta R that got a wave, I called it R. That's a name I associate when I notice that I have a symmetric situation. What do I get? Nu R transpose, ER transpose. I'll get VR 0, 0, 0, nu ER. As I expected, nu R was selected. It was selected because I didn't break charge. And I couldn't break charge. Remember, the same thing happened in the standard model. You cannot break T3 and U1 with one wave. That you cannot do. There is a linear combination which remains unbroken. That's what we did in the standard model. That linear combination we call the photon, the charge, the generator and the associated gauge field of photon. That's our choice. The same way that I called it, you know, this is the same thing. Remember that I call this guy neutrino. There is a convention when I call it a neutrino. I know relative charges. That choice of hypercharge is, you know, in SU2 charges are fixed, they are half minus half, but it's not like that when we add U1. So the convention, you see, it's one and the same convention. The convention that I use for hypercharge is the same that makes this guy neutral. Okay, if you wish, there were two fields. I didn't know what they were. You could have told me, how did you know that the upper field was? The way you reason is the following. You define the direction of symmetry breaking. You apply it on your field. Now I see that this is good that I call this neutrino because this guy got a mass here. It has to be neutral. Electron didn't get a mass. This might run a mass. The name electron is good. That's how I would proceed. I will see in my convention, for example, that this R couples to a photon. That will be in my convention. But nu R doesn't couple to the photon. That's a neutrino. Okay, this is very important to understand. The name is not in what you originally write down, in what in the world is. Originally, everything is equal to everything else. Okay, there is no neutrino or electron. W cannot distinguish neutrino from electron. Photon can do. So the name is in the beginning artificial. I'm guessing from the beginning. You know, when I give you this form, I actually specifying my convention that I will later choose to reflect what I've given to you. I should have called Q1, Q2. And then you and I will discuss and say, okay, let's use this convention. And that has to be consistent. And it will be, if you don't make a mistake. you will choose the formula for the, remember the formula was simple, Q was T3 plus Y. The arbitrary coefficient I call Y over 2. Then I make my convention so that the electron has charge -1 and so on, and that reflected on the Higgs field in a different level. It's good to, sorry, Nicholas.
These fields, delta R plus plus plus, are those eaten by the...
No, because they have doubly charged. Okay, you can say who is physical here. For example, does delta R plus exist? No, WR will eat it.
Because we can rotate, we have a gauge rotation, we can go on this.
Sure, we can. And you know how you reason in the standard model. Let me remind you. Phi was. You see how the questions that you took for granted because someone teaches you and you are listening and you pop up when you have to do it. When I did in the standard model, phi plus phi 0, I argued that this would be eaten by some notation, but think about it really. This can be eaten because W gets a mass. W can eat only the guy of the same charge. Charge is a good symmetry. If I carry charge +2, I cannot eat someone who carries charge plus that. I cannot mix. You know, what does it mean that they eat and they get mixed in the R gauge? Remember, there was some strange term between them, longitudinal components and so on. So the logic is, and this was VEV plus H plus IG. This is neutral. This can be eaten by, do I have a candidate? Yes, Z. Good. I go and check, but I first think whether it would work, okay? Then I say maybe Z will eat it, okay? I put a question mark, and then I do my rotation, and I see that they actually have a mass. So I reason here, where am I? I say delta R0 is VR plus some, I don't know, HR plus some IGR, this is just notation. Then I have delta R plus, nothing to expand, that's a physical field, and delta R plus plus. And then I go, I'm saying this will be the Higgs field, I'm sure. I go and check it, but I expect, I've seen in all previous examples when the guy gets a VEV, he gets this famous thing that MHR square is some lambda VR square. We always found that. Then I say, oh, this could be eaten by ZR. And maybe I'll get a massive ZR. I go and check that immediately, that's a chance. That's R plus. I have a candidate which is WR plus. Well, I chose this guy to be a triplet, so I'm hoping it will work, and the way it will work, I will go and check it, is that WR plus gets a mass, eats this guy. I will rotate it away. When I see the WR plus gets a mass, this guy here, I'm left with this. So this is the theory. I mean, love it or leave it. It's you know, it's like going for, invited for dinner, people from, what can you do? It has more states, unfortunately, okay? So we are just finding out, oh, I got rid of GR. Actually, I do eat it. And we do eat this guy. But we are predicting delta R plus plus. Immediately I predict delta L plus plus. Nobody can eat this guy either. Not only that, I predict delta L plus because there is nobody to eat this. This guy had a zero vacuum expectation value. Who can eat this guy? I also predict delta L0. I predict HR. So I predict the whole multiplet delta L. It will be heavy, of course. We didn't see it, it's somewhere at these TV energies, okay? And then there is this bi-doublet, which I called, which actually had two doublets. Tilde and so on, but there were two different doublets, okay? So from here I'm predicting the Higgs field of the standard model, plus another doublet, call it phi prime. A lot of values. They are related by quantum numbers, so the situation is not so messy. We shouldn't count the particles, we should count the representations. When you have representation, you have property, one and the same property, so it's not so bad. There is a triplet here, there is a doublet, I can deal with that.
Delta L plus plus will not be given, right?
Delta plus will not be hidden. This will be beautiful to predict this, to see these particles, because they have really beautiful manifestation. They produce pairs. There was this thing, you know, through the right-hand neutrino breaking lepton number. Here you see directly. These guys carry B minus L, so when delta R gets a vacuum expectation value, it breaks B minus L by 2 units. It breaks lepton number really, not baryon number. How do you know that it doesn't break baryon number? It doesn't couple to baryons. It cannot couple to quarks. Quarks carry color. We need to spend 1 or 2 or 3 lectures on this magical thing about color. You've heard from that from Alexei. I want to go through that. I want to discuss QCD, okay, next week. I will dedicate the whole week, I hope, to remind you how we saw the quarks and how really QCD works, confinement and all that, okay. Quarks carry color, therefore delta R doesn't couple to quarks, therefore baryon number is not broken. That's reassuring, because it's dangerous to break baryon number. We live a lot, it seems. You don't have to worry, but baryon number is dangerous, right? We will decay, but the limits are, it's not just us. Even from a human existence, Maurice Goldhaber put a limit many years ago. I mentioned this en passant. You remember roughly the number? From you and I living around 70 years, you can actually produce that number if you know the amount of radiation that would kill you quickly. What will happen if you decay? There'll be a lot of radiation, we will get cancer immediately. So he managed to put the first limit. He says, I feel it in my bones, where the proton lives. He got that to the 18 years. Impressive. So we cannot, you know, breaking a baryon number is a very dangerous thing. It should be very, very tiny breaking a baryon number. And then Super Kamiokande dedicated experiment. I have to talk about Super Kamiokande because they were looking for proton decay. You know the irony. They were devised to find proton decay, but they observed neutrino oscillations. In the 80s, nobody will give you money to look for neutrino oscillations. You could get money to do proton decay because everybody believed in proton decay and nobody neutrino mass. Now you cannot do an experiment on proton decay easily. So people that did neutrino oscillation, they would hide in the collaboration, they look for proton decay. Today you do the opposite. You look for proton decay, find yourself a collaboration that looks into neutrino properties. Well, I'm kidding. Now people also think about, but it's almost like that. Do you remember the limit? It's fantastic. They've done really an amazing job. For example, for this decay, the most interesting, the grand unification like pion positron. We went even to 35. When they stopped, they arrived to 35. 34 probably is other channels are closed there. Most of the channels are 10 to the 34, not all of them. This one's even 10 to the 35. So here we break the lepton number, it will manifest itself, as I said, into delta R minus minus, delta N minus minus, decaying into leptons. Either right, sorry, or left. There is something unique about the theory. This is I've chosen. This is the only predictive self-contained theory of neutrino mass. There will be hundreds of models you will see when you pop up and do something, okay? But this is similar in a way that the standard model treats charge fermions. Okay, you get predictions, okay? I can leave that just as an information. Okay. We can compute all kinds of decays related to neutrino mass. So in principle, see the right-hand neutrino. So I've tried to I've decided to give an extra lecture. That's why we did today. But I can see that you were in that. It seemed that I actually thought it's very good to do another example of symmetry breaking, not just some vector triplet exercise, but to take a theory, for example, working out grain unified theory, it's really beautiful. True, wrong or right, who cares? You would learn really how symmetry breaking works. The problem with the standard model is so easy, so simple, that you don't really learn any subtlety. It's sort of, it's kind of almost trivial, the Higgs mechanism. And leaves very little trace, right? There are these indirect things about Higgs decays related to masses. But everything that was interesting disappears and just the Higgs remains. Here actually you have the whole plethora of particles which are related to the Higgs mechanism. All their properties are related to each other. We would learn a lot about the Higgs in a theory beyond the standard model. Even more. I think I should, we have a few minutes for questions, okay? But I shouldn't start anything new. All I can tell you that the LHC there are two groups, Atlas and CMS, who are dedicated to the search of, they are even more, they are somehow more interesting to right-handed neutrinos, what I call right-handed neutrinos, I don't know how to call them, these ends, these new particles, okay, and associated physical processes. But there are interesting parallel studies trying to find these states. At the moment, there are only limits, which are in the hundreds of GeV. Now, the thing, maybe I won't say anything more about it, but this question was popping up, and it's not a new question, so I maybe just comment on that. When I say, when we speak of new particles that could exist within the theory, not in some new theory, for example, in the standard model, you ask me, well, what is the number of generations? Why do I say that I think it's 3? Well, I tell you, LHC didn't find them. Then you should tell me, or maybe they told me. I think someone maybe said, well, they could be heavy. After all, there are no zeros in experiment, right? All that the LHC is saying that the mass of the fourth generation is bigger than some number which come to, I think, 500-600. Let's say on the order of 500-600 GeV. You're saying, what's the problem? Maybe they weigh 950 GeV, so there is another generation you don't see. Associated neutrino is very heavy. Right? Or 2 TeV, or 75 TeV. So let me remind you, this is important when we speak of a theory. The mass of the fermion was Yukawa fermion times V. So that Yukawa fermion ended up being G over 2 M fermion over MW. And this is typical of any coupling in your theory that will be related to the vacuum expectation value. And this is very important to remember. When we speak of the standard model as electroweak theory, we should stress it's a perturbative theory. In other words, in order to confront it with experiment, I have to assume that it's perturbative, and then I do perturbation theory. That means that I assume that the couplings are small. And I do my perturbation, the way we did in QED. So what happened in QED, E squared over 4 pi turned out to be 137. Oh, great. Then I did G squared over 4 pi, the coupling, and I found it was 1 over 30 or something. Oh, great. This is small. When I got this energy, even G strong square over 4 pi turns out to be 1 over 10. You know, I'm checking the theory at LHC. Okay? I'm talking now about LHC, so I think, yeah, I can go on. This is a perturbative theory. Then I make my calculations and I confront it with the experiment. And we say that the theory is very successful because it's in perfect agreement to a percentage. But that can only work if couplings are small. So in other words, take the top quark. N top is 175 GeV roughly, which implies that you have a fermion. You get a factor of 2, which cancel this 2. G is roughly 1. 0.6 is 1 for me. It's roughly 1. And you can say, oh, wait, is this perturbative? Well, the physical coupling, let's call it alpha top, is Yukawa top square over 4 pi. So this is 1 over 4 pi. So this is roughly 1 over 10. It's okay. The top quark coupling is completely perturbative. We are lucky. Now let me now look at, in other words, what would be, so this is a half. But suppose that I have a new T prime, which is Yukawa T prime square over 4 pi. And we should have some agreement. This is not trivial now to put it a number like this, but roughly we get an idea. How big can it be so that the theory is perturbative? When this coupling is bigger than 1, you lose perturbativity. Or let's say, this works roughly as the rule of thumb. You really have to do the calculations, you have to do 2 loops, and you see where the perturbation brings you down. If you can remember it, that the effectively the coupling is just like alpha Q0. So in other words, the mass of a new generation should be less than a square root of 4 pi. Yukawa T prime should be less than square root of 4 pi. That's about what? 3? 4 maybe? So I can have a particle who is maybe 3 times, and this is dangerous, Lynn. You know, at this point you lose perturbation theory completely. And I speak that the standard model is 1% to 1,000 successful. Therefore, this is really a hard limit. Therefore, a new generation, if it weighs 3 times as much as the top quark, it's basically not perturbative anymore. At 600 GeV. This is why I kept telling you that the new generations would have to lie there for us at the LSE. This is simply the definition of the standard model. It has to be perturbative because nothing that I predicted would be correct. There will be loops with the heavy 2-3 loop, and each of them will contributing more and more, and everything I do would be accidentally correct. That's impossible. You now decided that you trust the standard model. I can bet anything that there will not be new in each generation. They will go on, of course. And they will try to put you limits. But you and I can be reassured by the high precision test of the standard model that this way we can explore and know where the new particles are lying. Which means also when I have a new theory like this one, these states I cannot send them where I want. You find WR, you have to find the states for me, you know. This is the beauty of your theory. If you get a mass through the Higgs mechanism at that scale, you have to live at that scale. Why? Because your mass is always proportional to that scale. And you cannot make the coupling infinitely large. You cannot escape. So we often say that the top quark is light. You know, top quark weighs 200 GeV, but we say light compared to the new scales of physics, which are maybe at TeVs or 10 to the 15 GeV. So we include in the top quark into the light particles. We define the light particles though that get, we say that the Higgs is light, that W is light with this new language of new scales. Okay. Nicolas had a question.
Rho parameter will change.
For example, rho parameter would be, okay, I'm glad you noticed. Everything will be changed, yes. Rho was 1 plus alpha over 4 pi. Something like this we got, right? Mt square over mw square. Great. There will be mt prime square. Now, oh, sorry. Catch. There will be a measure of SU2 breaking. It's going to be proportional. We found out when we did we didn't do the calculation. This can be done. I mean, this calculation is not so hard. Deciding these days about what to split for the take home and whatnot. And this is a nice little calculation that shows you how the renormalizability works. And therefore you could tell me, oh, maybe the fourth generation, unlike the third one, is very degenerate. You could still play with that. That would be okay. So I take it back. I was wrong.
Okay.
I could still save the raw parameter, but there were things which are proportional not just to the breaking of isospin of SU2, but the things which are directly proportional to the mass. So perturbativity will break down, but not in rho. Okay. So rho doesn't teach us. Not everything is equally sensitive to new scales. Okay. At this point, we use this 10 minutes. If there is no, there is a public question, we can turn this off, right?